Hello everyone, welcome to my talk. My name is Feilong Liu. I'm a fourth-year PhD student in the Ohio State University. Network bandwidth utilization is important. In parallel database system, plan fragments either get data by accessing local memory or get data by accessing remote memory through network. In a two-socket server, the memory bandwidth can be up to 150 GB per second, while for EDI InfiniBand, the network bandwidth is about 10 GB per second, which makes the remote memory access 15 times slower than the local memory access. Many queries are bottlenecked on the network bandwidth. Hence, shuffling needs to fully utilize the precious network bandwidth. How to fully utilize the precious network bandwidth? People have looked into RDMA. RDMA allows applications to access remote memory directly and bypass the operating system. RDMA supports two communication primitives. One is the shared memory primitive. In shared memory primitive, only one side posts the RDMA request. The other side is passive. For message passing primitive, both sides need to post RDMA request, and both nodes are active in the communication. RDMA has been extensively studied in the system community. Change work in EuroSys'17 leads to the question: How can we use one-sided RDMA primitive to help to accelerate analytical query execution? Kalia's work in OSDI-16 leads to a question: how can database system tolerate unreliable delivery? RDMA is also studied in database community. Puzzles in Sigmod 15 and VLDB-17 lead to the question: Is MPI good enough for the performance? How to accelerate all queries and not just join? Rodigan in VLDB-16 make us to ask the question: How to avoid contention for the communication multiplexer? This is the answer from our work. Can one-sided primitive help? Is unreliable delivery tolerable? Our work found that two-sided send and receive and unreliable delivery fully utilize the network bandwidth. Is MPI good enough? RDMA is 4 times faster than MPI. How can we accelerate all queries? Can we avoid contention for the communication multiplexer? In our work, we design an RDMA-aware shuffling operator for all queries. And the shuffling operator uses multiple endpoints to avoid thread contention. Now let me give you a background for parallel database system. Data is partitioned and distributed across all nodes. However, as data is in different nodes now, tuples with the same join key may not be in the same node. Matching tuples need to be brought together. Database system map SQL query into query plan. This is a query plan for a join query. Parallel database system cut the query plan into plan fragments, with each fragment communicate with shuffling operator, and each shuffling operator is a pair of send and receive operators. There are two communication patterns for the shuffling operator. One is repartition. In repartition, both tables are repartitioned within the cluster. This is an example of range repartition the tables. For this tuple, the join key is B, which belongs to node 0, and it sends node 0 using the shuffling operator. We do the same for the rest of the tuples. After we finish the repartition, all tuples with the same join key are in the same node. We can do join locally. The other communication pattern is broadcast. In broadcast, we choose to broadcast a smaller table, so that every node will have a whole copy of this table. Here we show an example of broadcast R0. All tuples in R0 are sent to every other node. After we finish this communication, every node will have a whole copy of R0. We can do a join locally. In our work, we design an RDMA-aware data shuffling operator for parallel database systems. There are two challenges in implementing the RDMA-aware shuffling operator. The first challenge is to isolate the complexity of RDMA. RDMA is very complicated. It can only access register memory. The shuffling operator needs to manage the memory registration. It also needs to handle the packets arriving out of order. It needs to support different implementations, such as RDMA, MPI, IP over IP, so as to compare each alternative choice. The second challenge is to identify promising design choices. We compare both two-sided and one-sided primitives. We also consider both unreliable datagram and reliable connection transport, so as to balance between the number of Q pairs and thread contention. We introduce an endpoint abstraction to hide the complexity of RDMA communication. The endpoint offers a uniform abstraction for communication. One shuffle operator can have one or multiple endpoints. The send operator first calls the getFree function to get a free buffer from the endpoint. After populating the buffer, it calls the send function to send buffer out. The receive operator calls the getData function to get a buffer with data. After consuming the data, it calls the release function to return the buffer to the endpoint. All functions are thread safe. We consider three design choices and map them into three dimensions. The first dimension is the RDMA transport, unreliable datagram or reliable connection. The second one is RDMA primitive, RDMA read or RDMA send receive. The third one is how many endpoints per operator, one single endpoint or multiple endpoints. As for RDMA transport, in unreliable datagram, packets may arrive out of order or get lost. However, database systems frequently do not care about the packet arrival order because there is no notion of order in relation model. In InfiniBand, packet loss is rare. Hence, unreliable datagram is acceptable for database systems. Prior work shows that unreliable datagram has better scalability and uses fewer Q pairs for communication. However, reliable connection can save CPU cycles because it supports larger message size, posts far fewer RDMA requests. RDMA read can save CPU cycles because only one side is active. However, it cannot work with unreliable datagram, which leaves us fewer implementation choices. The number of endpoints used is a trade-off between thread contention and number of Q pairs. We can choose to have one single endpoint shared by all the threads, or have multiple endpoints with each thread having its own endpoint. No design choice is strictly better than the others. We choose to implement all the design choices. However, as we have shown, RDMA read does not work with unreliable datagram, which leaves us 6 algorithms to implement. In the evaluation, we develop a multi-thread parallel query engine. We implement all combinations of design choices and evaluate it with FDR and InfiniBand. We compare with MPI and IPYB. We first do an overall comparison of the algorithms. We use 16 nodes from both FDR and ADR InfiniBand and compare both repartition and broadcast algorithms. The vertical axis is the receive throughput. The higher the bar, the better the performance is. RDMA is 4 times faster than MPI when working in 16-node broadcast and ADR InfiniBand. The two send and receive algorithms work well across all settings. In the following comparison, we are going to focus on these two algorithms. How many queue pairs are needed for communication? We use 16 nodes from the ADR InfiniBand for evaluation. We change the number of queue pairs by changing the number of endpoints from single endpoint to multiple endpoints. The horizontal axis is the number of queue pairs. The vertical axis is the receive throughput. The unreliable datagram achieves better performance with fewer queue pairs. Moreover, unreliable datagram has better scalability because the number of queue pairs is constant for the unreliable datagram, while the number of queue pairs is proportional to the cluster size for reliable connection. So far, we have shown the shuffling throughput. How does the shuffling algorithm affect query response time? We turn to TPC-H queries. TPC-H is a benchmark widely used in database research and has some very complex queries. This is a query plan for TPC-H Q10. It has 1 aggregation, 3 joins, and 5 shuffle operators. We choose to evaluate with TPC-H Q3, Q4, and Q10, which shuffles a large amount of data. Every node stores 100 GB of data in memory. We choose to use 2 to 16 nodes in the ADR InfiniBand for evaluation. We use the RDMA algorithm, which shows good performance and better scalability, which is multiple endpoint send and receive over unreliable datagram. The baseline is MPI. The vertical axis is the response time. The lower response time means better performance. We first compare the local execution and RDMA algorithm for Q4. The RDMA algorithm shows close performance to the local execution, which means RDMA algorithm can overlap the communication and computation. Please see the paper for additional experiments. What's the scalability of the different algorithms? The result shows that the RDMA algorithm has better scalability for all 3 queries. For Q10, working with 16 nodes, the RDMA-aware shuffling is 2 times faster than the MPI algorithm. To our knowledge, this is the first work showing that the transport level choice can affect the response time so significantly. In conclusion, two-sided send and receive and unreliable delivery fully utilize the network bandwidth in database system. We propose the endpoint abstraction to hide RDMA details, and we design a shuffle operator with multiple endpoints to avoid thread contention. And our shuffle operator accelerates TPC queries by 2 times. You can access our code in the following link. Thank you for attention. I'm ready for questions.